yet?
Yeah.
Hi, talk away.
Okay. Well, I'm sorry for all this mix up here. I'm going to talk about minimal volume hyperbolic 3-manifolds with cusps and compare the orderability of their fundamental groups. So first of all, I wanted to dedicate this talk to the memory of Patrick d'Aulnoy, who discovered some time ago that the braid groups are left orderable. And that got me interested in ordered groups. And this talk is about ordering the groups of minimal volume hyperbolic 3-manifolds. A left ordering a group is a strict total ordering of its elements that's invariant under left multiplication. So if G is less than H, then FG is less than FH for all FG and H in the group. It's a very common thing. For example, 3-manifold groups, as long as the first Betty number is positive, a 3-manifold group is left orderable. All dot groups are left orderable, for example. A left order can be turned into a right invariant ordering in a simple way. But if an ordering is both left and right invariant, we'll call it a bi-ordering. And that's an even more stronger condition on a group. Next slide. If you have a left ordering, the positive cone is a set of all elements bigger than the identity.
Oh, I screwed that up.
That's okay.
Yeah, my pad there. All right.
The positive cone set is closed under multiplication, and every group element is either in the positive cone or its element inverse is in the positive cone, or it's the identity. And conversely, if you have a sub-semigroup satisfying 1 and 2, you can define a left ordering by saying F is less than G, if and only if. Let me move that up a little bit.
Okay. You want the next one down? Okay.
Yeah. You say G is less than H if and only if H inverse G is in that set P, and that defines, is quite easy to check that that's a transitive and left invariant ordering. It'll be a bi-ordering if that positive cone is also normal. That is, if conjugate of anything in P is in P. Next slide, please.
Okay.
Yeah. Okay. Next slide. If you have a left order or a bi-ordering on a group, the group has very special properties. For example, if you look at the group ring R of G, where R has no zero divisors, then R of G also has no zero divisors. That's conjectured to be true for torsion-free groups, which left ordering implies torsion-free, but not conversely. But that's an open question yet. Also, there are no next slide. The only units are the trivial ones, consisting of RG with R a unit of RNG group element. That's not true for torsion-free groups, and there's recently shown counterexamples to that. Next. A bi-order group has unique roots, meaning if F and G have equal nth powers, then they must be themselves equal. That's a very strong property. And also there's no generalized torsion. A generalized torsion element is an element so that some non-trivial product of its conjugates is the identity.
Oops, get a little bit. Ah, darn it. There.
Those orderability properties are local properties, meaning that a group has the property if and only if its finitely generated subgroups have it. Next. For abelian groups, being biorderable is equivalent to being torsion-free. Typically, for example, Z squared, you have uncountably many different orderings. If you look at them as the integral points in the plane, you take any non-zero vector and look at the dot product of an element of that with that product and order them according to that magnitude. That's a biordering, and there's uncountably many different ones. In fact, it's the theorem that a group has either finitely many orders, possibly zero, or uncountably infinitely many. There's no groups with countably infinitely many left orders. Next. There are many torsion-free non-abelian groups which fail to be left orderable. We'll see some in later slide. Next.
Oh, darn it.
Oh, dear.
I can't keep, I should have opened it in something right here.
Okay, now the theorem, free groups are biorderable. Next.
Okay.
To see this, look at the lower central series. The descending series of subgroups defined by Fi plus 1 is generated by commutators of F with Fi, the previous one. And it's well known that the infinite intersection of these is simply the identity, and the lower central quotients, Fi mod Fi plus 1, Fi plus 1 is normal in Fi. They're finally generated free abelian groups. So you can choose the biordering for each of those quotients. Next. And we'll call an element positive, a non-identity element, if you look at the last Fi in which it survives, and if it's positive in that chosen ordering of Fi mod Fi plus 1, then we'll call it positive. Otherwise, it's not. So that defines a positive cone, and it's fairly easy to check that that's a two-sided ordering of the free group. Next. And that we call those, I'll call that a standard ordering of the free group, and there are many others. Well, there's uncountably many of these, but also many others too. Next. The braid group acts on the free group Fn by automorphisms. And it's actually a faithful representation from the braid group to the automorphism group of Fn. And next. On the generator F sigma I of the Artin group sends xi plus 1 to xi, xi to xi plus 1 conjugated by xi, and the other xj's are fixed. This just describes the action of the braid on the punctured disk and on its fundamental group, which is a free group on n elements. Next. Now I'm going to call a braid order preserving if there's a biordering of the free group Fn preserved by beta. That is, x is less than y in the free group, if and only if its image under beta, x beta is less than y to the beta. Next. So clearly the identity braid is order preserving. Inverse of an ordering preserving braid is also order preserving. But it's not necessarily true that the product of two order preserving braids is order preserving, because they may preserve different orderings. Next.
Okay, let's see. Right. There we go.
Now, the generator sigma I claim, is not order preserving. To see this, assume that it is. Next.
Right.
If there were a biordering preserved by sigma I, assume that xi is less than xi plus 1. Otherwise, take the reverse of that ordering. And if we apply sigma I, we conclude that xi plus 1 conjugated by xi is less than xi. But that would then imply that xi plus 1 is less than xi, which is a contradiction. On the other hand, every pure braid is order preserving. To see that, you note that a pure N braid acts on the abelianization of F by the identity. And then you check that is also acting by the identity on all the other lower central quotients. So it preserves every standard ordering of F, the way we defined it. As a corollary, the square sigma I squared of an Artin generator is order preserving. And every braid has a power which is order preserving, because some power of it will be a pure braid. Next. Now, if you take a braid, you can look at its closure, which is a link, and then also include the axis, and I'll call this the braided link, which is the closure together with the axis. And you see that that's really the fundamental group of that, complement of that, is really the mapping cylinder of the braid action on fundamental group. So the theorem is that a braid is order preserving if and only if the braided link has biorderable fundamental group of its complement. Next. Okay. As a corollary, a braid is order preserving if and only if every conjugate is order preserving, if and only if its product with full twist is order preserving, because you get the same braided link. Next. Now, if you have two braids, possibly a different number of strands, but their braided links have homeomorphic complements, then beta is order preserving if and only if gamma is. Next. Now, if a link has an unknotted component, then as this picture shows, you can cut open the disc that it bounds, give it a full twist, and then put it back together. And it results in a homeomorphism of the link complement, but the link itself might change, as you can see in this picture. Yeah, next. An application of this is that the braid sigma 1, sigma 2 up to sigma k times sigma 1 is order preserving. Next. Yeah. So here we've got the braided link sigma 1, sigma 2 on the left, and that curve that's darkened, if you do a number of disc twists, you get the picture on the right, and that gives you the braid sigma 1, sigma 2, sigma 3, in this case sigma 1, and they have homeomorphic complements. So since the one on the braid sigma 1, sigma 2 is sigma 1 squared is order preserving, so is the one on the right. Next. Now I want to talk about hyperbolic 3 manifolds. Okay, next. Now, Gabai, Meyerhoff, and Milley prove that there's a unique closed minimal volume orientable hyperbolic 3-manifold. It's the Weeks manifold obtained by 5(1) and 5/2 surgery on the Whitehead link. Next. There's a picture of the Whitehead, two different pictures of the Whitehead link. Next. Now, Danny Caligari and Nathan Dunfield showed that the Weeks manifold, it has a fundamental group which is torsion free, but is not left orderable. In fact, they showed a stronger result that is not even so-called circularly orderable, which I haven't discussed. But next. Now, if we look at a one cusp hyperbolic orientable 3-manifold, there's actually two examples. One is the figure 8 non-complement, and the other is its sibling, which is obtained from the Whitehead link by 5(1) surgery on one component. Next. The fundamental group of the figure 8 complement is biorderable. That was actually shown quite a few years ago by myself and a colleague in France. But the sibling fundamental group is not biorderable, although it is left orderable because it has positive Betti number. Next. Both those examples are realized as fibrations over the circle. And for the figure 8 complement, there's two positive eigenvalues for the monodromy, which implies biorderability. On the other hand, biorderability would imply at least one eigenvalue should be positive, but the sibling next has two negative real eigenvalues. So that group cannot be biorderable. On the other hand, it is left orderable. Next. Yeah, maybe one more. That was so awkward.
That's all right.
Ian Agel proved that a minimal volume 2 cusp orientable hyperbolic 3-manifold is either the Whitehead link complement or the complement of the -238 pretzel link. Next. Now, Eiko Kin and I proved that the fundamental group of the Whitehead link complement is biorderable. It's by an explicit calculation. But I'm going to use the braid ordering theory now to argue that the fundamental group of the complement of the -238 pretzel link is not biorderable. Next. So look at the 5 braid, sigma 1 cubed, sigma 2, sigma 3, sigma 4. It's braided link, which is figure 1 there. If you fiddle with that, you see that it's actually equivalent to the -238 pretzel link, which is the figure 4. Next. On the other hand, that braid, sigma 1 cubed, sigma 2, sigma 3, sigma 4, is not order preserving. Next. We see that actually by a calculation, argued by contradiction, as in the case of the Artin generator sigma I. Next. Yeah, now look at these links, these minimally twisted chains of 3, 4, 5, and 6 components. It was proved that in the case of 4 cusp, the minimal volume hyperbolic 3-manifold with 4 cusps is homeomorphic to the complement of C4 in that picture. And I'm going to argue next that that complement is biorderable.
Oh, did it again, buddy.
Oh dear.
That's all right. I know we're kind of where we were.
Yeah. Right. So if you look at the braid sigma 1 to the -2, sigma 2 squared, that's its braided link is pictured on the right, number 1. If we do a disk twist on that darkened component, you get something which turns out to be that 4 chain. Now, since the link, the braid is a pure braid that we started with, that's the complement of that link, and also the link on the right, number 3, has biorderable fundamental group. So that shows the 4 cusp case. For 5 cusps, it's conjectured that the complement of C5 has minimal volume among hyperbolic 5 cusp orientable 3 manifolds. Next. And I claim that its complement is also biorderable. Next. That's gotten by looking at the braided link of sigma 1 inverse squared, sigma 2 to the -2, sigma 3 to the -2. You just fiddle with that and see that that's equivalent to C5. Next. And similarly, the complement of C6 has biorderable fundamental group as it's homeomorphic to, I don't know if you see it there, sigma 1 to the -2, sigma 2 to the -2, sigma 3 to the -2, sigma 4 to the -2. Next. Now I'm going to end with a 3 cusp case. S3 minus that 3 chain is Cameron Gord and his co-author Wu called it the magic manifold because it has some wonderful properties. It's conjectured to be the minimal volume 3 cusp orientable hyperbolic 3 manifold. Now, I don't know if that's biorderable or not. That's its complement is homeomorphic to the complement of sigma 1 squared, sigma 2 to the -2. And that's next. I don't know if it's biorderable. And equivalently is the 3 braid sigma 1 squared, sigma 2 inverse, order preserving. And that's it. Thank you very much.
Let's thank Dale for all the efforts.